Hey, welcome to today's video. I'm Prof. Omar. Today we have a treat for you where we're going to talk about Mobius inversion, which is an interesting concept, and we're going to look particularly at it in the lens of number theory. And we're going to look at it from a different light than is usually presented. Instead of defining what a Mobius function is, we're going to develop Mobius inversion from something that already existed in the first place. So this is going to be following what is outlined on the Caltech Harvey Mudd Math Competition 2013, so that's CHMMC. This is a contest that's usually taken in teams by high school students. And the reason I wanted to go over this particular problem is I happen to be a professor at Harvey Mudd, and this is a collaborative video where the first two problems on the actual contest were presented by the channel Mu Prime Math. And the presenter there actually is a student at Caltech, so it's a cool Caltech Harvey Mudd collaboration. All right, so let's actually dive into the mathematics of the problem. So the way we're going to define the Mobius function is different than what is usually done. We're going to develop properties of it from the way we define it. So the Mobius function mu is a function that's defined on the positive integers, and it is defined as follows. It's 1 at the value 1, and then for any other positive integer n, the sum of the values of mu applied to divisors of n, which include n itself, is 0. Okay, so it seems like at face value that this doesn't really define what mu is, but we'll see by looking at special cases that it actually does. So let's start with a prime number. Okay, so what is mu applied to a prime number? So according to this recursive formula here, mu of 1 plus mu of the prime p is going to be 0 because the only factors of p when p is prime are 1 and p itself. Now we already have that mu of 1 is 1, so this value here is actually a 1. And so that tells us then that mu of a prime is negative 1. So we'll keep that at our disposal right there. Okay, cool. All right, what about the square of a prime? So the factors of the square of a prime are 1, the prime, and the prime squared. There are no other factors. So according to our recursive formula again, mu of 1 plus mu of p plus mu of p squared is 0. Okay, and we already know the values of these two. We know that this is 1, and we calculated just earlier that this is negative 1. And so this thing has to be 0. And so we get that mu of the square of any prime is 0. All right, so that's our second example. And then finally, what about the product of two primes? So we can do the same process that we did here. The product of two primes has 4 possible factors. 1, the number itself, and then the individual primes p1 and p2. Okay. And so we get mu of 1 plus mu of p1 plus mu of p2 plus mu of p1, p2 has to be 0. And we have the information that mu of 1 is 1. And from what we developed in our first example, mu of these individual primes is negative 1. And so that tells us that this has to be 1. So mu of the product of two primes, or maybe I'll write it in the same color, mu of the product of two primes, distinct primes, is 1. Okay. All right, cool. So we get a feeling for what this function is doing on some types of numbers, and we're not sure what it's doing in general. All right, so I'm going to talk later on in this video about what the Mobius function actually can do for you, which is something that's actually discussed a little bit, but not specifically for the Mobius function, in the first video that's actually presented on Mu Prime Math, which talks about those first two problems on the CHMMC 2013. All right, but we're gonna, in this video, develop what mu has to be for any integer n at all. Okay, and we have some cases here, so we're going to dive in and see what happens with other types of integers. So the problem on the CHMMC actually first discusses what to do when you have mu applied to a product of primes where the primes are distinct, right? So this is a product of L distinct prime factors. And we have some hints. We've done some work to show that mu of a prime is 1 and mu of the product of 2 primes is -1. So what I want to do is play with the product of 3 primes and then see if we can come up with a conjecture. Okay, so if we're looking at the product of 3 primes, lots of factors here. And we get from our recursive formula that we have a relationship between mu applied to these factors. So here, the factors are 1, P1, P2, and P3. And then the product of pairs of these, and then the product of all 3. So there's 8 factors in total. Okay, so according to the information we have that mu of 1 plus mu of P1 plus mu of P2 plus mu of P3, and then plus mu of these products of pairs of primes, there's 3 of those, and then plus mu of the product of all 3 primes is 0. Okay, so let's actually clump these together and organize them, because if we're going to do this for a product of a generic number of L primes, then maybe we can get an idea of what to do in general using this idea with the 3 primes. So this value here is 1. Okay, and these values are actually -1 and +1 here. So we get a -1, -1, -1, and then here we get a 1, 1, 1. And so to balance things out, this value here has to be a -1. So mu of the product of 3 distinct primes is -1. So we see that the number of distinct primes we have makes like the sign of this negative flip. If we have 1, we get -1. 2, we get 1, and 3, we get -1. So it seems in general, maybe, that our conjecture is that this value here is -1 to the number of primes in our list. But of course, the question is, how do you actually go about proving this? So the base case would be when L is 1, and we've established that this actually works in the base case. And so the question is what to do in the inductive step, given that we're given the hint to do this by induction. Now, the first thing we notice is that the factors of a number like this are all numbers that are products of distinct primes. So we'll be able to use the inductive hypothesis on those fewer primes in our product that we have. And then also we can kind of figure out how this thing is going to look like in general. So we'll have something like this. So we'll have mu of, maybe I'll actually get rid of all of this to look at what happens in general. But it seems like from the case of 3 primes, what we should do is clump based on the number of primes we're taking products of when looking at the sum that we have. So we have mu of 1. And then we have mu of the individual primes, of which there are L of. Okay, then we have the product of pairs of primes, which starts at P1, P2, and then ends at the last pair, which is PL minus 1 PL. Then we have triples, which is P1, P2, P3, up to the last set, which is mu of PL minus 1, minus 2, PL minus 3, PL minus, let's try that again. PL minus 2, PL minus 1, PL, etc., all the way down to mu of P1 all the way to PL. Okay, now all of these here involve the function mu applied to products of primes where we have fewer than L primes, so we can use our inductive hypothesis. So here, we'll get a contribution of -1 to the 1. And here, we'll get a contribution of -1 squared, and the number of times we see it is exactly L. And I want to think about this as actually L choose 1. And the reason to think about that is we're selecting in each case one of the L primes in our summand. And that'll help us when we think about what happens in the next step. Okay, so to fix this, this should be a 0. This should be a 1. And this should be a 2, actually, in the exponent. So let's do that. Okay, and then here we'll have an L choose 2 because they're exactly L choose 2 ways of selecting a pair of primes. Then we'll have L choose 3 times -1 to the 3, etc. And then this unknown quantity that we don't know yet. Okay, and we know that the sum of all of these things is 0. So if we clump all of these things here together, we get that 0 has to equal the sum in this red box right here, which is -1 to the 0, plus L choose 1, -1 to the 1, plus L choose 2, -1 squared, all the way to whatever the penultimate thing is here, which is going to be L choose L minus 1, -1 to the L minus 1. And then plus mu of P1 up to PL, which is the thing that we don't know. Okay, so luckily for us, this entire expression on the left actually looks very close to a binomial theorem. So if we actually took this piece here, copied it, then this quantity here, if we added in L choose L times -1 to the L, we'd actually get by that binomial theorem that this is 1 plus -1 to the L, which actually is 0. Okay, so 0 is this entire quantity here, and 0 is also this entire quantity here. So these two summands at the end have to be the same. And so we actually do get that mu of the product of the first of these n or these L distinct primes is -1 to the L, which is the thing that we thought it was in our inductive hypothesis. So kind of cool that the binomial theorem comes seemingly out of nowhere. But it sort of appears because we're looking at all of these products of primes involved that are primes from the list P1 through PL. Okay, cool. So now we know what to do with products of primes. The question that remains is how to determine what mu of n is in general. Okay, so here we have the statement, determine mu of n when n's prime factorization contains at least one repeated prime factor, and then summarize the results in general for what mu of n is for any integer n. Okay, so we're going to actually prove something really interesting that's sort of surprising, that isn't necessarily the way that one would go about this if they were doing the contest, but it's actually a really interesting phenomenon, number theoretically. Okay, so again, our defining expression tells us something kind of fascinating, and I want to make a lemma that actually claims the following. If you have two positive integers m and n, whose GCD is 1, then I claim that mu of mn is mu of m times mu of n. Okay, so why would something like that be helpful? Well, what this tells us then is that if you have a general positive integer, let's say n, you know n can be written as the product of powers of primes. Then, according to this, if we use it inductively, mu of this positive integer n is going to be, well, I guess I'll use lowercase n since we have that in our original statement, is going to be mu of p1 to the k1 up to mu of pl to the kl. And so what that means is that if we want to figure out what mu of n is for a general positive integer n, we can just look at powers of primes and then see what the consequence is on this entire expression. Now, interestingly enough, we could have used this to prove this expression right here, but it was kind of cool to just do it using the binomial theorem. And what I mean by we could have used this to prove this is you can think about this as p1 to the 1, p1, t2 to the 1, pl to the 1. And so we could have done that here with the exponents being 1. All right, so let's go ahead and actually give this proof, which is actually going to be quite interesting. So the proof is going to be inductive. I won't prove the base case, and I'll leave that for you. And so what I'll do is assume this is true. And what I mean by this is true is I mean this expression here for all pairs of, I'll use the word coprime, which means that they have this property of having GCD1, integers m1, m2 with m1 and m2 less than some specific positive integer n. So we're assuming that this quantity holds inductively for smaller values, and then we want to see what happens with a particular value n. Okay. So what I mean here is we're thinking of n as the product of two numbers. So to make the idea a little bit clearer, maybe let's say this is true for positive integers d1, d2 that have no common factors, and we're claiming this statement is true for pairs of positive integers d1 and d2 where d1 and d2 are less than this particular n that we have. Okay, so now let's say we had the product of two things, a and b, that actually equal this fixed positive integer n, and we're trying to prove that mu of ab is equal to mu of a, mu of b. How would we go about doing that? Well, the only thing that we have at our disposal is this definition of what mu is. So we know that if you sum over all divisors of AB of mu of D, you get 0. Okay, but we can break this up. I'll write the 0 on the left-hand side here. And we'll break this up as a sum of two things, d1 dividing A and d2 dividing B of mu of D, 1 d2. Now, the reason we can do this is because A and B have no common factors here, we're assuming. And so the factors of AB are factors of A multiplied by factors of B. Okay, so now we can write this as a sum, d1 dividing A, d2 dividing B, and we'll take this whole sum where d1 and d2 is less than AB, so we don't include that last factor where d1 is A and d2 is B, of mu of d1, d2, plus mu of AB. That's the only thing that's left out of this sum. Okay, cool. So why is something like this useful? Well, if we instead if we look at this expression here, this is mu of a product of two things, d1 and d2, where d1 is a factor of A and d2 is a factor of B. But A and B have no common factors, so that means d1 and d2 have no common factors. So by our inductive hypothesis, this is actually mu of d1 times mu of d2. Okay, so we can compare this to another thing that we know is 0, which is the sum over d1 dividing A of mu of d1 times the sum d2 dividing B of mu of d2. And the reason we know that this is 0 is the individual products ends are 0 themselves. Okay, so if we do that, this is the sum over all d1 dividing A and then d2 dividing b of mu of d1 d2, which we can then split, or the product, sorry, so mu of d1 mu of d2, and then we can omit when d1 d2 is actually exactly ab, and then the only thing that's missing is mu of the product of a and the product of b. Okay, so if we look at what we have 0 is equal to this entire summand plus this, but it's also equal to this entire summand, which is the same as this thing, plus this. So these two things here have to be equal, and so mu of AB actually is mu of A times mu of B. Okay, so that's kind of a cool way to go about this interesting fact. And it establishes then that we have this lemma proven. And so now we can use the lemma to prove or determine what mu of n is in general. Let's actually erase all of this stuff and go ahead and work out what that ought to be. So the first thing we noted is that what really only matters is what happens on each prime power in the factorization of a given positive integer. Because now by the multiplicativity, we get this fact right over here. So let's look at what happens when you have a particular prime power. So we know mu of 1 is 1, and we know mu of a prime is negative 1, and we calculated that mu of the square of a prime is 0. So what happens afterward? Well, you can kind of see what happens. So if you take the cube of a prime, by the expression that we had before, mu of 1 plus mu of p plus mu of p2, or p1 squared plus mu of p1 cubed has to be 0. This is 1, this is negative 1, and this is 0. And so that means this has to be 0 as well. So this is kind of cascading effect, and I won't write this down rigorously, but if you wanted to figure out what mu of the power of any prime is, I'll go up to p1 to the k minus 1 and mu of p1 to the k. Imagine repeating this process inductively. You'd have this being 1, this being negative 1, this being 0, and a cascading effect that makes all of these 0. But this entire sum is 0, and so that would make this 0 as well. So really what you're getting here is that mu of p1 to any power, a prime to any power, is 1 if that power is 0. It's negative 1 if that power is 1. And it's 0 otherwise, if that power is greater than or equal to 2. Okay, so this 0 actually makes a huge effect, because what it means is when we go to this product formula that we proved a little earlier, anytime you have a number that has the power of a prime appearing with an exponent at least 2, another word for that is a number that's not square free, it has a square of a prime in its factorization, then mu of it has to be 0, because mu of that specific prime raised to that power that's at least 2 is going to be 0, and by the multiplicativity you get 0 for mu of n. So what that means is really the only numbers that you have to concern yourself with are these numbers right over here that are products of primes that only have one particular prime appearing in the prime factorization. We don't have a higher power. Okay, so that tells us then that we do have a formula in general. We can write it up here. And that formula is that mu of n is negative 1 to the L if n is the product of distinct primes, is 1 if n is 1, and then is 0 otherwise. It's kind of a cool phenomenon. Now, a question that you might ask is like, where does this mu function even come into play? And it plays a big role in number theory itself. Usually, it's defined like this. And then properties like this recursive formula that we have on top come as a consequence if you're taking an elementary number theory or introductory number theory course. But if you're learning about Mobius inversion on general partially ordered sets, this is a much more natural characterization. And there are lots of different things that are going on there that we won't talk about here, but maybe talk about in future videos. Okay, so where do we go from here? Well, the video that was discussed earlier on mu prime math really talked about what's called the Dirichlet convolution of functions. And that is this phenomenon here where if you have two functions whose domain are positive integers, then the convolution is this function defined sort of number theoretically as the sum over all divisors of n of f of k, g of n over k. Okay, and the big thing that you can do as a consequence of this together with the Mobius inversion we talked about before is if you have a function g that's defined as a sum of a function f over divisors of n, so g of any n is the sum over divisors of n of f, then there's a relationship where you can actually invert this. And it says that f of n is the sum over k divides n of g of k times this mu function, mu n over k. Okay. And the reason that this comes up has to do with a relationship to this particular Dirichlet convolution that we have right over here. Okay, so what does that tell you then? So it allows you to manage with things like this, being able to invert and calculate the individual functions themselves. So you can give this a try with this particular example that was an example on the CHMMC. And it says there exists a function f such that the sum over k dividing n of, this should be f of k, is n squared for all positive integers n, using what we know about Dirichlet convolutions, which is really this consequence right over here, and this mu function that we developed, and this is the mu function we talked about earlier, find f of 2 to the 4, 3 to the 4. So actually give this a try knowing this thing that we developed right over here. So that's a nice summary of this Mobius inversion. An interesting place in which it comes up when we're looking at summative functions like this one over here and how to invert it, using that to actually compute something like this example right over here. And we'll see in future videos how this comes up in a lot of different contexts outside of just number theory. So I hope you enjoyed today's video. If you did, definitely click the like button. And if you want to see more videos like this, definitely subscribe to the channel.